parts of the brain that do something. So let's start with this one. So these are not spaces. These are not places. You can't point to it. These are jobs. These are functions. So these are not a place in the brain. These are things the brain can do. So we're going to be talking about 3 of them tonight that you have to understand. We'll list them all first. First one has a variety of names. We will give it one. Activating system. Depending on who you talk to, this is the usual name. It's called the reticular activating system. For the rest of your life, you don't have to write that. You can abbreviate it as your RAS. So on a test, you can write RAS. I'm with you. That does that one. All right, next one we're going to learn tonight is the basal ganglia. If you look in Saladin, he will not list that. He has a different word. What does he use as a different word? Basal nuclei. That's the synonym. So depending on who you talk to, it's either basal ganglia or basal nuclei. I don't care. Pick one. Basal something. And the last one we're going to talk about is the limbic system. So again, these are not places. These are things that your brain can do. But they are located different spots. So I'm going to show you the reticular activating system first. This is in the brainstem and the mesencephalon. Someone remind me where your brainstem and mesencephalon were. Where were they? At the bottom or the top?
The top.
The bottom of the brain, primitive function, right? The job of this is to activate the upper brain. All right, so it's supposed to turn on your brain, activate your brain. So I'm going to show you a picture, and I'm going to show you why that matters. This is not supposed to be something you have to draw. You don't have to draw this. If you want to, go for it. Okay, so those dots represent the parts of the RAS. So again, it's not a single thing. It's not a lobe. It's a bunch of stuff. So to get your bearings, medulla, right? Pons, mesencephalon. These black things, which have all those funny words you don't have to know, are different parts of the RAS, the RAS, the reticular activating system. Its job is to wake up the brain. So let's review what's in these things. What does the pons do? Bridges, right? What do the peduncles do? Track. So these are all the information coming up my body. Hit these, and if you remember your 231, which all of you should, can someone remind me what serotonin, norepinephrine, what those things are? Neurotransmitters. And what do neurotransmitters do?
Convey messages.
They convey messages. So let's review. Serotonin, was that an inhibitory, excitatory neurotransmitter? Inhibitory. How about norepinephrine? Could be both, right? So if you think about it, the signals are coming up my body, hitting these things, and sometimes they get turned on, and sometimes they get turned off. So this thing can control what keeps going. So it can wake up my brain, or it can activate my brain, or it can filter. It filters consciousness. Okay, that sounds really hippy-drippy, right? But when you're asleep, what are you aware of when you're asleep? Anything? Say no, nothing, right? That's called sleeping, right? The alarm clock goes, and immediately you wake up, and then you're aware of the bed and the sunlight. How did that happen? What did the alarm clock do to wake up your brain? It turned on this. When the alarm clock goes up, the RAS begins to send messages up to my brain to become conscious of my body. Right? So when you're asleep, that turns off and nothing gets to your brain. When you wake up, it turns on and begins to send messages to your brain. How many of you can feel your shoes right now? Say none. Put down your hands. Right? Why am I not feeling my shoes? Because that filters that my shoes never get to my brain. Right? So as my shoe information goes up my spine, it simply gets filtered out by the RAS. Why does my brain have to be aware of my shoes? It doesn't. Right? So in a hospital setting, what do we call people who can't get their brain to turn on? What are you in? Coma. So congratulations, you now understand the concept of coma. If I turn off your RAS, you don't wake up forever. right? So the purpose of the RAS is to wake up my brain and get information to be consciously perceived, constantly aware. So I put you in a coma, I could rip off your legs. You won't know it in theory, right? Maybe you will. But this is to tell my brain what to pay attention to and what not to pay attention to. Filters out information. Make sense? So RAS is how you wake up in the morning, how you pay attention. My goal as a teacher is to keep your RAS going, so you pay attention to what's going on, right? There's a reason I have you write notes. Writing with your hand increases RAS activity. So your brain gets more signal from writing than just watching the PowerPoint that none of you would remember. Make sense? All right. So that's the RAS. Its job is to wake up your brain, keep your brain on. Make sense? So now if I give you neurotransmitters, I can adjust how much you filter. That's how the doctors are going to do that. They can put you in a coma by turning off the RAS chemically, and then you can't wake up. Make sense? That's the RAS, basic awareness. But there's something else we're going to do next. We're going to do the basal ganglia next. We're going to spend longer on them than this. Let's go to our basal ganglia. Let's turn off the picture. Why am I going over there? Over here. Basal ganglia. Let's talk about them. All right. Its job. Motor algorithms. Did I spell algorithm right? Did I spell algorithm? Okay, good. Okay, let's break down each of these words. What does motor mean? Movement. So it's about something about making you move. Okay, computer junkies. What's an algorithm? Anyone that learned algorithms in science class?
Series of yes or no.
Very good. A series of commands, right? A series of choices. So algorithms are a sequence of commands. Okay. So I'm going to give you a silly non-anatomical analogy. When you hit print on your computer, right? What does the printer have to do to actually print something? What's it have to do when you hit the print button? Does it have to turn on? Then it has to put the paper in, right? A little inkjet comes out, and jams twice, right, in my house. Hey, so when I want the printer to do something, there's a sequence of commands it has to do. It has to turn on, load the paper, move the ink, and all that stuff for it to actually do the motoring I want, right? So when you want to motor, there's a sequence of things you have to do. So I'm going to walk that way. Someone tell me the sequence of commands it would take to get me to walk there. I'm waiting for you.
Pick up a foot.
Which foot should I pick up?
Your right foot.
Okay, now what?
Move forward, like pull it forward.
Be quick here. My cerebellum's not good.
Extend your right
Okay,
foot.
put it down. I
Pick
didn't
up
go anywhere. Let's try this again. Lift right foot.
Extend your right.
Extend right foot.
Lean forward.
Lean forward. Okay, my arms should be doing something. Stand 100%, right? Lift foot, right? Right. But you get the idea. So when your brain says walk across the hall, there's a whole sequence of commands you have to bring up, algorithms, to tell you how to do that. The last thing your frontal lobe said was walk. The basal ganglia then crank out the algorithms to make walk happen, lifting your feet, putting your head down. Right? So when you take notes, all your brain says is write the word. And your basal ganglia figured out how to make your arm go the right direction. Make sense? Just like your printer spool. Right? So your basal ganglia's job is to basically come up with the commands to make a motor happen. So let's do that. There are two commands you can have, two pathways, which we're going to learn because thou shalt know them, thou shalt. Two pathways. There are two things your basal ganglia can do. One is called the direct pathway. The direct pathway excites muscles. In English, turns them on, makes them go, contract. All right? So the direct pathway turns on the muscles. Can anyone guess what the other choice is going to be? Hazard me a guess.
Indirect.
Indirect. Very good, because we're biologists. We're the simple people. So indirect pathway. What do you think an indirect pathway does to the muscles?
Turns them off.
Turns them off, relaxes, inhibits. So when I want to walk across the floor here, and maybe you could get it right, I have to tell my right leg to contract, but my left leg not to. Now my right leg has to stop, and my left leg has to go. So I have to tell the muscles to go on and go off in sequence for this to work. And that's a basal ganglial system. Make sense? Okay, so now we're going to show you some pictures and videos of the basal ganglia, this command algorithmic sequence. So I'm going to show you the static picture first, just because I will, which is right here. So, no, don't draw this. Okay? These are the parts of your basal ganglia. You don't have to know them. It'd be nice if you did, but you don't have to. So they have all sorts of fancy Latin names, black stuff, right, whatever. So those are the parts that are going to tell my body how to do the algorithms for what I decide to move. So when I decide to walk, those parts calculate the sequencing and send out the images, the signals, the pathways. All right? So what I'm going to do is show you a different picture here that will really bother you a lot, which is, oops, sorry, wrong way. This one here. Here is a picture. You don't have to take a picture of this on your phone, right? This is showing the interconnecteds of the basal ganglia. So these parts are the basal ganglia, and those lines tell it to excite or inhibit. So why do I need both sets of lines? Okay, want to take a guess?
For both pathways?
Both pathways, right? I have to tell things to go and things to stop. So I'm going to use different types of neurotransmitters to tell us different parts to turn on, turn off. So I can tell your thalamus to go or your thalamus to stop. The thalamus would switch the body to the different motor units. Make sense? So it's a complex series of ons and offs, just like hitting your printer button has to tell things to go on and off. Right, so we're going to do that. We are going to make my brain do that. All right, so down here is my thoughts. I want to move, motivation. Here are the basal ganglia, the little algorithm generator. And then down over here is my movement, because that's my spinal cord to my muscles. All right? So, motor programming, they call it. Motor sequencing, motor algorithmics. All right, so it makes a bunch of signals like that. Here we go. I want to grab a ball. Why? I don't know. It just does. Okay, so I'm thinking I want to grab the ball. It's the last thing my frontal lobe does. Sends the information to my basal ganglia, who are going to come up with how to grab a ball. So what would it take to grab a ball? What would I have to motor to grab a ball? What are the steps? Lift my arm, extend hand, open hand, grab, right? So those are the sequences, the algorithms the basal ganglia would create to have me do that. So we're going to do that. By doing this. So I say, grab ye ball. I send that information to my basal ganglia. My basal ganglia then does a bunch of interesting voodoo, and then I'm going to start turning on my spinal cord to grab the ball. I'm going to activate the direct pathway to extend. Right? But now, I want to let go of the ball or stop grabbing the ball. Now I have to do the indirect pathway to turn off these muscles. Right? So I'm going to go through and I'm going to turn off my motor cortex. That way I don't grab the ball anymore by going through the algorithm. Ever do that where you can try to hit cancel print right on your computer and it spits out 15 more pages? Right? That's this. I'm trying to cancel the movement by going the indirect pathway. So when you hit print, you're doing direct. When you hit cancel print, you're doing indirect. But both of those are necessary to grab the ball and let it go. Yes?
What do these look like in babies? Are they smaller or?
No, they're just less synapses between them. So a baby, well, we can't ask them, right? But they still have them, they still function, but because their motor cortex isn't asking for a lot more things yet, then the sequencing has been, that's why babies need to try to do stuff. That way they learn the sequence algorithm. If you pack your kid in a car seat all their life, they'll never walk right? Because they'll never get the algorithm of what it takes to walk. So you crawl, then you walk. That's part of your brain learning the algorithm to make that happen. Right? So we can go through here. And then I stop. Yay, thank you. Make sense? So now I'm going to screw this up. I'm going to mess up this process. So here's the normal cheesy animation for this. So we have our basal ganglia. Here's what my brain's thinking. Here's what my body's doing. And I'm just doing that, right? So I have indirect and direct pathways. I'm going to mess up one of them. I'm going to put a lesion right here on the substantia nigra of the dopaminic pathway. Okay? Boom. What changed in my basal ganglia?
The
Is it the
amount
same as
going
before?
from the cortex.
Let's go back. So look here. Now look. What do you
Got
see?
excited.
So this one changed to a lot more of these, there's more of those, more of those. So I changed the balance in this basal ganglia, right? So if I mess up my basal ganglia, it's going to change how my algorithms work, right? So let's think about that. Let's go back to the board real fast, turn this guy off. Let's think about a disease at the nursing home that you're probably taking care of right now. That would be a problem in the direct pathway. What would happen if I could not do the direct pathway? What would I do when I wanted to walk? I wouldn't walk, right? So what disease in the nursing home is when people try to do something and they lock up or can't move? Parkinson's disease. You've now learned why Parkinson's does what it does. So in Parkinson's disease, you stop the direct pathway. So the patient wants to walk and nothing happens because I hit print, but the commands don't go. So nothing happens. I can't get my muscles to walk. Right? They lock up, they sit there, they stall. Make sense? And they can't go. So there's another one. Let's pretend I damage your indirect pathway instead. What would I see in a patient whose indirect pathway is damaged? They move all the time. What disease is that where you keep moving all the time, uncontrollably? What's an H? Genetic disease. Huntington's disease. In Huntington's disease, you can't stop your muscles. They constantly go because there's no way to turn off the algorithm. The printer just keeps printing, right? So in these diseases, these are basal ganglia problems. The person's brain's fine, but they get the wrong coding to their muscles. So they can't go when they want to, they can't stop when they want to. All right? Make sense? So basal ganglia problems are a problem getting the muscles either turn on or turn off. All right? Make sense? It's basal ganglia problems. Make sense on basal ganglia? That's controlling that. So to show you I'm not making this up much, I'm going to show you a picture of what I just told you. Here. This is showing the basal ganglia again, right down here. Showing the neurotransmitters that you forgot about since last term. And the black lines are ways I can screw up your life by blocking those pathways. Because every time I block a pathway, I'm changing how the algorithms for motor control work. So in Parkinson's, I stop the dopaminergic system here, which means I can't start the signal up there. Therefore, you can't get going. You stall. In Huntington's, I'm blocking the inhibitory signal here, which means I can't turn off what's going on up there. So I constantly keep going. Right? Make sense? So your brain is saying one thing, and you either can't stop or start the motor that's occurring. It's a basal ganglia. So in a stroke of the frontal lobe, you just can't go at all. But in damage to these, you go incorrectly. You either go too much or go too little from what you're thinking. Make sense? All right. Questions on basal ganglial pathways. And no, you don't have to quote the pathway. If you can, it's great, but you don't have to. Make sense on basal ganglia, basal nuclei, motor control, extrapyramidal control. Cool. If you remember your neurotransmitters right, this one turns on, this one turns off. So you see how there's a balance between ons and offs to make it go on and make it turn off. Question on basal ganglia? Not at all. Clues. All right. The last one of these integrative areas is your limbic system, which you can't see in the dark. Your limbic system. Let's try it. Limbic system is for emotions and memories and cravings, also called choices. All right. So this system is dealing with the emotional part of your life. Do I feel happy or sad? Deals with the emotions, the memories of those. How did my birthday party make me feel? And also deals with a thing called cravings or choices. So let's put this together. So you have a good birthday party one day because your parents are nice. So you have a memory of a really good first birthday party. That makes you feel happy. So next time you're invited to a birthday party, what do you want to do? I want to go. I crave going. I am interested. I'm sort of choosing to go. because these three things are connected. So you had a biology teacher at one time in high school who made a really bad class, which gave you a bad memory, which means you hate science, and now you chose not to become a science major, right? That's the logic of this system. So those three things act as a unit. What I feel and what I remember will decide what I do. I became a biology major because I got A's in biology, made me feel good. I didn't want to be a biology major, right? I just couldn't pass math, right? So that was the logic. Make sense? So your limbic system's job is to coordinate these feelings and memories and these craving emotional things. So I'm going to show you a picture of them, and then we're going to do a little bit more on it. Let me show you a picture of your limbic system. Again, it's a system, it's not a thing. It's a bunch of things, right? So you have a couple things you know, these two you don't. So PCC says, thou shalt know the amygdala and the hippocampus specifically. So we have to write those over here. Does anyone know what your amygdala is for?
Emotions?
Emotions, very good. So the amygdala, that's the emotional part of the limbic system. That's one where you remember the feeling, where the feeling is residing. Hippocampus. Does anyone know from Psychology 101 what your hippocampus is for? That's the memory part of the brain. And they're both together in the same unit, right? So where were you on 9/11? I'm going to hit both of those. You're going to remember where you were 9/11 and how that made you feel. That's why both of them pop up with a memory, right? Make sense? Okay, so then I'm going to show you now is how this sort of relates to the rest of you. So if you were in Afghanistan and you got shot at and half blown up, you'll have a memory of that, right? So when you're here and you hear a backfire in a car, what emotion would you have?
Terror.
Terror, and what would you do if you heard the backfire and you had terror as emotion? What do we call that?
PTSD.
PTSD is relating your memories at the front correspond to your emotions now, right? That's the logic behind it. So because they work as a unit. Make sense? So my job as a teacher is to make you stop hating science. I hopefully give you a good memory. Although I give you quizzes and you cry. I get that. I understand it. Right? But that's the idea behind these two. So I'm going to show you a little video on your limbic system. It's not too long. Let me show you. This will start kind of here. It's going to take a minute here.
This is this video that Fritz Heider made in the 1940s. They actually cut out these little cardboard shapes and moved them frame by frame on a lights table. This is before digital video. And if you just show this to a normal observer and ask them to tell you what they saw, they will come up with a social description. They will say, well, this large triangle picked on the little one got away, then the large one got really angry at the end, broke the box, etc.
Okay, so as he'll go on to explain longer, there's no, those are just shapes on a screen, right? But why did you have that emotional response that the little one got sad and the big one got mad? Because memory. At some point, you associate yourself with one of them. I got beat up as a little triangle, and then I got mad, right? So one thing your limbic system does is take things you experience now and try to match it to things you lived with before and give you the same emotional impact and craving, right? So think of peer pressure. You care about what your peers are doing then, and you also care about what your peers are doing now because that helps you connect and relate emotionally to them, right? That's that logic behind it. You have the same memories, and therefore you get the same kind of emotional impact. Make sense? All right, so your limbic system does things like that, about making an emotion, a story, that kind of stuff. So what we're going to do is we're going to zip ahead here a little bit to right about here.
That we're responsible for love and for hate and for being conscientious and diligent. You could just feel people's bumps on their skull and tell something about their personality from this. Well, of course, that was completely wrong. But some of the basic idea that parts of the brain are specialized for certain cognitive functions was actually right. What maps onto particular parts of the brain are more simple and in many ways more abstract kinds of things. Language, memory, decisions.
The trolley problem.
Yeah, there we go. Yeah, that's good.
Runaway trolley. 4 men in its path. All of them will die. But wait, you can pull a lever. You can change the trolley's course to another track where only one man stands. You have a choice. Kill 1 or let 4 die. What are you going to do?
Tell me what your answer is.
Kill one.
Let's see if that's
I would pull it. I'd pull the lever and divert the train.
Yes, I would absolutely pull the switch.
Most people say, yes, that's a morally right thing to do, because what you're doing is essentially the utilitarian thing.
That means having 1 person die isn't as bad as having 4 people die.
Absolutely. You're saving 4 lives. There's another equivalent scenario.
Same situation. Runaway trolley. 4 men will die. But this time you're on a bridge. And there's a man there. He's fat. Fat enough to stop the trolley and save the 4 men. But he won't jump. He'll need to be pushed. Can you push the man over the edge?
You're gonna push the guy? So here's the problem. You notice how you're feeling a little more uncomfortable here, right? That's your limbic system. Your limbic system is trying to make an emotional value to your choice. You have to choose to push him or not. That comes out of the limbic system, right? So your limbic system says, that doesn't feel good, I don't like that choice. This choice feels good, I'm gonna do that one. So even something like this, your limbic system is the one that's having to evaluate your feelings, your memories, how you were raised, and come up with a craving or a choice criteria. When I raise my children, I want them to be moral people because I want their limbic system to make the correct feel good, feel bad when they make a choice, right? That's what parenting is, believe it or not. Okay. So let's try this.
I don't think that would be a possibility at all.
And I don't think this would be justified.
I can't do that.
Most people say, no, that's not an appropriate thing to do. This is a real mystery because the outcomes are the same. If all you really care about is what is the consequences of your action, you should feel morally at ease with pushing the person off the bridge if you felt at ease with flipping the switch before. Every moment of our life, our brain is making hundreds of decisions for us. We have to compute all the things in our environment that have value, and then make decisions about essentially all our preferences. We need to understand what the biological basis of that is. We need to understand how it is that neurons in our brain are producing those kinds of decisions. Economics begins with the understanding that our desire is essentially infinite and the resources are finite. And so we have to make a decision.
Neuroeconomics is basically trying to combine the powerful mathematics of economics with the careful observation and nuance about human nature in, say, psychology. We're interested in how emotion influences economic decisions and how we can measure that and understand it. Imagine how great it would be to be able to go to the floor of the New York Stock Exchange and simultaneously measure brain activity with lots of traders at the same time and measure, in a sense, the heart and the mind of the market, almost literally. We can't go to the floor of the exchange and put every trader in a 6-ton fMRI magnet. But you could take one subject at a time and scan their brains.
Position this, right about like that. And I'm going to get you to relax back with your head right here.
fMRI is essentially an enormous magnet that you're inside. It operates simply by measuring differences in blood flow in your brain. So where the blood flows, the thoughts go.
So remember that with stroke, right? Hypometabolism meant the cells weren't working. So logic is the more blood, the more ATP, the more cells are working. Make sense? So by measuring blood, you indirectly know which parts of the brain.
They're tightly linked.
One of the major tools is just to do an experiment. So we use something called the ultimatum game.
The ultimatum game. Two people, total strangers, A and B. A is given $10 and has to share some with person B. So A has to make B an offer. B gets to decide if she is going to accept or reject. If B accepts, they both get to keep their share. But if B rejects, nobody gets to keep the money, and they both lose.
In the ultimatum game, if you're a little too greedy and you don't offer quite enough, nobody gets anything. So it's a kind of revenge that costs you a little bit of money to punish somebody you think has been greedy or unfair or violated a social norm of sharing. Neuroscientists have actually put people in an fMRI to play the ultimatum game. And what happens is, it makes kind of a nice simple story about what the brain is doing when people face an unfair offer. That there's activity in a brain area called the insula. That's an area that's involved in expressing bodily discomfort, like hunger, disgusting smells, pain.
Okay, so the insula is not one you have to know, but that's also in the limbic system. So when you are looking at these three choices, which one do you want to go visit or do? Do you want the trash, the pain, or the Whopper with cheese? I think it's this one, right? If you're the same person. So your insula, your limbic system says, I have all these choices. This one makes me feel bad. This one makes me feel bad. That one makes me feel good. So I'm going to go that one, right? So the choices you make are based on the emotional memory you had. So if you had a really good experience with trash cans, you might choose that, right? But since most of us had a good experience with food, we tend to hear one. So if you are smoking a cigarette, right? The reason you keep craving the smoking is not the dopamine, is that you had such a good feeling with the cigarette, your limbic system keeps pulling you to choose that again because the memory, the emotion are so good, you want to do it again. That's the craving of addiction, right? The more you do stuff that feels good, the more you want to keep doing good, therefore you keep picking the bad habit you shouldn't be doing, right? Make sense? Think of a donut. A donut tastes good. I remember good donuts. I want every donut I've ever seen, right? Even though I know they're bad for me. Right? So your limbic system is partly making this choice that I want something, not the other. So not giving me the money made me feel bad. I'm going to choose that differently. Make sense?
All those areas activate the insula. So when people say that offer is disgustingly low, the same brain area is active as is active when you smell a disgusting odor.
The Ellsberg paradox.
One of the things we're interested in neuroeconomics is risk. So one of the tools we use to study is something called the Ellsberg paradox, which is an experiment devised by Daniel Ellsberg in the 60s. And Ellsberg was interested in people's willingness to gamble in the face of known or unknown odds.
A lot of them.
2 fists. Each contains red and blue marbles. You must gamble on what color marble you will draw. The catch is, in the right fist, you know there are 5 red marbles and 5 blue marbles. In the left fist, you don't know the combination of the marbles. Which fist will you gamble on?
Which one are you going to bet on?
Right.
Imagine that.
5 reds, 5 blues. I want to play with that hand.
That one.
It looks like this fist is the best bet, but in reality, this fist should be every bit as good of a bet as this fist.
People show what's called ambiguity aversion, which is that just averse to the lack of information. If there's something that's ambiguous, something where you would need to acquire more information before you can even make a decision, there's parts in your brain that will inhibit your behavior.
When we studied this in fMRI, we found a lot of activity in the amygdala, which is a fear, emotional memory, learning area of the brain. The brain doesn't like being forced to act in ambiguous situations, so when confronted with them and asked about choices, the amygdala transmits a kind of vigilance or caution signal to the orbitofrontal cortex, which causes people to say, I'd rather not bet.
Economists have been fascinated by this because it looks irrational. You should have some kind of expectation, but we didn't evolve to pick out balls. We evolved not to get killed. And if there's a dark region there, a cave or a dark forest, with something that's potentially lethal, but they have no idea what could potentially be there, you better have a mechanism in place that just says, don't even go there.
So this kind of finding is at the heart of what neuroeconomics is about. In financial markets that may affect things like deciding not to buy stocks that you've never heard of, in voting for politicians, a familiar name might make people feel more comfortable. In trying new products, people might avoid a brand new product, reflecting a kind of fear or sort of paralysis in the face of the economic unknown.
All right. So let's pause there for teaching and learning. So, if I am a good teacher, which you could argue maybe I'm not, what would I need to do to make sure you don't do the ambiguity aversion in this class? What is something a teacher should do to make sure you don't end up being totally paralyzed by indecision?
Make a syllabus.
Besides the syllabus, which I'm supposed to do anyway by law. There's something, I say 4 words, I put a big graph up, don't I? What are those words? Thou, shalt, no, that's 3 words. Okay, 3 words, I can't count. Thou shalt, yeah, okay, right. So there's a reason I say thou shalt know, is so that way your amygdala knows that's on your test. There's no, if you ever say, guess what I'm thinking, that's a bad way to teach, because your amygdala would say, I don't even know what to do because I don't know what he's talking about. So the clearer I can make the chart that thou shalt know, the less ambiguity aversion you'll have. You'll find it easier to remember. Make sense?
So you're talking about lab and how you don't know which model to look at.
So you take a picture at all of them.
Yeah.
So I tell you, all these ones will be on here. That way you don't know, try to guess which one. Right? So in your clinical exams, which are timed, by the way, when you become a nurse, you have 2 hours to do the questions. If you don't know the answer to question 1, what should you do? Move on, because you will spend 20 minutes worrying about the answer you don't know and fail your clinicals. So one thing you have to do as a student is learn to get over the ambiguity aversion. If you don't know, keep going. Damn the torpedoes, full steam ahead. I've seen students go 20 minutes on question 1 on a test, because they didn't know the answer, they just sat there in Ellsberg being worried about it, and you fail. Does that make sense? So as future nursing professionals, you're going to have lots of ambiguity in your life. You have to either figure out how to get over it or deal with this Ellsberg paradox. You're going to be paralyzed until you figure it out. Make sense? So you got to work on controlling your amygdala. But its job is to keep you from going in a dark alley if you don't know what's there. Because your ancestor did that and died. Right? That's part of the choices you make. Do I choose to go there or not? So we're going to do one more little thing on choices.
One of the areas that has really yet to become informed by brain science is moral decision-making. Moral decision-making is hard. It involves making choices where oftentimes both alternatives aren't very good. And so we have to pick the best of the worst scenario to do.
A lot of previous experiments in moral decision-making involved as-if experiments.
Experimenters put people in this hypothetical situation, but we think that those kind of experiments are kind of unreal because people don't make an actual decision.
We really hope to be able to see how people, when there's real stakes at risk, how they actually behave, how they actually go about having to make a real decision that has real moral consequences.
We kind of thought, what's the worst thing we could make people do? What's like the hardest moral decision? And we kind of came up with taking food from a child, right?
Just laughing about it.
And then we thought, okay, well, what's worse than that? Taking food from a child from an orphanage.
We decided to set up an experiment that involved real orphans in a orphanage in Africa. It really allows us, by having real stakes, to see how people make real moral decisions.
So the limbic system is remembering all your memories about kids in orphanages, how you felt about them, how to make the choice that you're going to do by taking their food away. So think about your future in healthcare. You have to make choices for patients, right? At some point.
Okay, let me tell you a little bit about the study. This is a study on moral decision making. In particular, you're going to be making donations to a charity in Africa. This is a brochure that contains a description of the charity as well as all the children. These are real children from a real organization, so it's important to remember that your choices will have an impact.
In our experiment, we have two scenarios.
So in one case, we give people a choice between donating to one child a certain number of meals or 2 kids with a certain number of meals each for those 2 kids. If you choose to give to the 1 kid, then the 2 kids gets no meals. If you give to the 2 kids, then the 1 kid gets no meals.
We also have what we call the take scenario, where we take away meals from kids. At the beginning of the experiment, we endowed each of the kids with a certain amount of meals, and subjects will be making decisions about taking away from those meals. So they have to make a decision: do I take 10 meals away from this kid, or do I take 6 and 6 meals away from those 2 kids? And that makes the decision even harder, because now they will be harming kids because they're taking away meals.
Some people find these choices very difficult and very, very emotionally conflicting.
There's no way to give without taking away some of the meals?
Right, we ask you to make both decisions to give meals and take away meals.
It seems pretty arbitrary, a way to decide how much food to give each child.
Right, so you are asked quite morally hard choices to make, but these are choices we ask you to make.
Okay.
There's the limbic system in there trying to figure this one out, right?
There's some belongs in here that remove all metal from your body. We never had anybody walk out on us and leave the experiment, but people got really involved, and I had people afterwards told me, wow, this is like one of the hardest decisions that I ever had to do. Okay, there's his ring. Alright, I'm gonna start the actual experiment now.
I did begin to develop a sense of what I'm doing is going to make an impact, positive here and negative here.
It was hard. It was really hard. I felt really guilty.
Sitting there, watching this little screen with that little symbol, that little ball, you almost feel like you're dropping a bomb from a mile above somebody.
From an economic perspective, it's a decision that's made every day millions of times, but it's not one that I personally make very often.
Yeah, she's one of the more fairness-minded or equity-minded people that we've seen.
I was definitely trying to be as fair as possible because, well, first of all, to have to make the choice to begin with isn't fair.
Yeah, she chose to take more meals from 2 kids rather than taking fewer meals from 1 kid.
People seem to find the give scenario more rewarding than the take scenario, not surprisingly. So when they find out that if they're giving meals to the children, their reward areas like the orbitofrontal cortex is activated. Whereas in the take scenario, they find that quite unpleasant. So here we see insular activity.
This subject seemed to be switching a lot between the 2 different options, showing that he has a lot of internal conflict, as opposed to other subjects who kind of like follow a set of rules that they came up with.
My rule was to save as many kids as you can, but occasionally the pictures of the kids did impact me emotionally. Even as I was making the decision, I was thinking, I'm violating my own rule here, because she looked so cute, and she was so young, and the other kids maybe looked a little older.
I think moral and economic decision-making are related.
It clearly shares some of the mechanisms.
We can assign values even to those moral decisions, and then once we assign values, we have numbers, and then the brain can just treat them in the same way as an economic decision.
When it comes down to it, when we're making a moral decision, ultimately what we're doing is making some kind of value-based decision. And so the way of thinking about those values in a quantitative way will likely lead us back to economics.
In order to split things relatively evenly, I was willing to give up about 15 to 20% of the total, but not more than that.
I was just so busy trying to figure out how can I keep from taking from any child, and there's no way to do that.
I think he settled on disregarding the number of children he helps. So in this case, he's probably going to switch the lever and, well, maybe not. He's not. The predictions are off. The predictions are really off for this. Maybe he's one of the types who really doesn't want to make the choice, so he just lets the computer, in some sense, make the choice for him.
I did. At the end, I let the computer go. Just let it go because it was too much of a choice, you know. You look at this face, wow, he could eat, he should eat, you know. But you look at these two, well, maybe they're a little malnourished, can use a little more, you know. I wouldn't want to ever have to make that decision.
Okay, you're done with the experiment. We're going to come in and take you out.
In our economic life, we're deeply concerned with how do we make decisions about things that have different values to us. In our moral life, we think about what are our moral values. Now that we understand that the brain is essentially a value machine, that it's using calculations with value all the way up from very basic processes to moral processes, it really suggests now a new, in a way, kind of unified principle for understanding how the brain operates.
Let me tell you what it took away, right? So, as future healthcare professionals, right, you're going to encounter choices all day long. That's based upon your memories and your emotional values. So, when you get to study for your test or go to your child's birthday party, which one do you pick? It's a rhetorical question. You don't have to answer it, right? But your choice depends on this limbic system's desire here. So your choice is based upon the combination of how would flunking biology make me feel versus having my child cry, right? That's the choice you're making. Make sense? So any choice you make is basically in the limbic system's job to decide based on emotions, memories. Make sense? So if you hate me now, it's in your limbic system, and you'll always hate me forever. Make sense? But now we're going to tie this into one more concept, which is what the limbic system would do to your body once you make those choices. So we have one more little stretch of thought here. If I take my emotions and memories and choices, they will affect the body. If you don't believe me, get stressed out and tell me how you feel. Right? So we're going to see what that is. Over here, our next topic for today, the main one actually, is the autonomic nervous system. And so we're going to spend the rest of the day. Squeaky thing. So can someone tell me what autonomic is talking about? What do you think that sounds like? Automatic. This is involuntary body organs. Is the autonomic nervous system is dealing with the involuntary body organs. So not your skeletal muscles, not my talking, but things are involuntary. So name some stuff that's involuntary in your body. Heart, digestion, tears, right? All these things, glands. So we're talking about those kind of things. So when I have an experience, that's going to tell my involuntary organs to be affected in some way. So there's two choices here. Our nervous system. One option, one way they can respond is called the sympathetic response, or sympathetic system. Does anyone know the other choice? Parasympathetic system. So when I have an emotional memory, when I think about whatever, my body is going to do one of these two choices. To remember them in this class, you're going to remember fight or flight is how we remember this sympathetic system. What does it mean to fight or flight? What are you doing? I have to either kill you or run away, right? So you're in a dark alley, someone jumps you, you either kill him or you run like hell, but that's your choice, right? The other one we remember as rest and digest. Those are the only two choices you have for your involuntary organs. So when the veteran has PTSD, which one do you think his body is choosing to do?
Sympathetic.
Sympathetic. I'm back in Afghanistan. I'm going to fight or run. Right? That's why his body's acting that way. It's because the memory kicks on the sympathetic response. Your goal is to get him to be more parasympathetic. Make sense? So anything that would make me scared, stressed, anxious, like this class, I'm going to be in sympathetic mode when I remember how I felt. Anything that's going to make me sleepy or want to eat will be over here. Make sense? So every involuntary organ will be affected by these two systems. So what we're going to do is we're going to do something out of your packet of pain. So get out your packet of pain. You have a little chart to fill in. It's not this one. Turn that down, go here. Boom. So I'm going to fill in some of these with you, and I'm going to turn you loose to do some others. But this is a chart that thou shalt know. 3 words, I just learned that. Right? Because you're supposed to know what each system will do to each organ. All right? Let's go through this page 12, by the way. Look at the organs over here. These are involuntary organs. My pupils, my sweat glands, my blood vessels. These are not things I can control. This is involuntary, subconscious stuff. I can either make it fight or flight, or I can make it rest and digest. So pupils. When you get scared, when I attack you in an alley, what do your pupils do? Dilate, get bigger, expand, up arrow. This is for you to study. I don't care what you put. But they're going to get bigger. So I can put a dilate. You can put an up arrow. You can put expand. Pick a word you like. I don't care what word you put. Your mom ever say white with fright? Your eyes got big with fright? That's the logic behind it. Why would you want big pupils if I'm attacking you in an alley?
More light.
More light so I can see you to kill you with, right? I have to survive. All right, so what do you think your pupils do when you're half asleep in front of the couch? Constrict, normal, less. Down arrow, less dilated. Pick a word that you'll remember for a week. So my eyes get big when I'm scared, they get smaller when I'm resting. Make sense? Notice how they're opposites. That's the logic. You have 2 choices, they're opposite of each other. All right, let's try this one. Let's go down to sweat glands for laughs. What do you do when you're nervous up here in your project? What will sweat do? Increase, right? You get sweaty when you're scared. You get sweaty when you're nervous. You increase sweat. What happens when you're resting and digesting to your sweat? Decrease, less. Remember, they're opposites, so it's just reverse. Less, normal, pick a word you prefer. All right? Let's do another one together. Let's do heart, down here. When you are scared, your heart should what? Beat faster, increase, right? Your heart's thumping out of your chest because I need a heart to pump blood to kill you with. Right? What does your heart do when you're resting and digesting? Normal, less relaxed. So white coat syndrome, when your patients are scared of the doctor, they have a high pulse. Because they're scared of you, their heart does this. You give them a pill, they go home, they don't need the pill. But you gave them a pill anyway, right? Because their heart was excited because they're scared to death of you. Make sense? So they're in sympathetic mode. Your job is to fill in the rest of the table. You have 5 minutes and we'll talk about it. Find a friend, find a text, find Dr. Google.